Okay, so now we want to turn our attention towards exponents and logarithms. So first, I want to kind of go over just the basic properties of exponents. So hopefully some of this will be kind of review, but if not, I think it's important to kind of establish these as a baseline first. And then we'll get into logarithms, which are the inverse functions of the exponents. So first of all, with an exponent, just of course, just the basic definition, of course, with an exponent, we could think of it as repeated multiplication, right? So we have our base, which in this case is 2, and then our exponent, which in this case is 3, right? Sometimes we call this a power. Sometimes, like in this case, we would call this, when we raise it to the third power, we would say that this is 2 cubed. And if we're raising something to the second power, we would say that it's squared, right? We've seen this before. And that just, again, the name for that just comes from the fact that if you had a square, then the area of it would be the side length to the second power, right? So that's why we call it squared. And then same thing for why we call it cubed, is because it would give you the volume of a cube. So let's just go through some of the basic properties that we can put together with these exponents here. So the first one is called the product rule. And we're going to have all of these same properties for logarithms, right? So it's important to look at them for exponents first. So the product rule is so named because we're looking at the product of two numbers raised to an exponent, specifically the same number. So like as an example to start with, if we have 2 to the third times 2 to the fifth, we can actually just figure out what this is just using the definition of an exponent, right? So 2 to the third is 2 times 2 times 2. 2 to the fifth is 2 times 2 times 2 times 2 times 2. So regrouping everything, technically using the associative property of multiplication here, right, which says that we can reorder the parentheses. We can see now there's 8 copies of 2, so we get 2 to the 8th. Okay. So in general, if we have, say, a to the n times a to the m, this will be a times a times a, right, n times a times a m times whatever m and n happen to be. All together, we're going to have m plus n copies of a, right? So in other words, if we're multiplying two things with the same base raised to an exponent, we can add the exponents together, okay? Now we're only showing it for whole numbers here, but this will extend to any kind of exponent. So it could be rational numbers, negative numbers, whatever the exponents happen to be. And we'll talk about what exactly those kind of exponents even are later on in this video. But this is not restricted to whole numbers. Okay, now similar to the product rule is the quotient rule. Right, naturally we're going to have a rule for division as well. So if we have something like, again, if we just start with some concrete numbers here and just see what the answer happens to be. So on the top, we can see this is 2 times 2 times 2 times 2 times 2. And on the bottom, this is 2 times 2 times 2. So we can see how many copies of these cancel out. Okay. And then what we're left with is 2 squared. So in general, if we have m copies of a on the top, okay, so like a to the m divided by a to the n again. If we have m copies of a, then we can cancel out n of them. So we're going to be left with a to the m minus n. Okay, so this is the actual quotient rule here. And of course, we're going to have the restriction that a can't be 0 in this case. That's always going to be true whenever we have a denominator. Okay. So let me just highlight what the actual rule is on both of these to make them easily accessible here. Okay. So this is the product rule. This is the quotient rule. Okay, and then we'll keep going. Okay, so next up we have the power rule, which is really just an extension of the product rule. Okay, so if we have something like x squared to the third, okay, well, using the definition of exponents for this outer part, we can see this is x squared times x squared times x squared, right? And then applying the product rule, this tells us that this is x to the 2 plus 2 plus 2, in other words, 2 times 3. Okay. So ultimately what we're doing is we're multiplying the two exponents to combine them into one exponent. Okay, so we get x to the 6th here. So in general, if we have a to the m to the n, we get a to the m times n. Okay, so this is known as the power rule. Okay, so this next one, sometimes it's called the power rule, sometimes it's not really given a name. So I'll just keep it under this same category here. So if this is x times y, say to like the third power or something like that, then we can think of what this would be. Again, xy times xy times xy. Now, using the associative properties and the commutative properties of multiplication, we can rearrange everything here because all we're doing is multiplying, right? So we can rearrange this into x times x times x times y times y times y. And we can see this is x to the third times y to the third. Okay. So in other words, we can cube everything inside of the parentheses here. So in general, if you have a times b to the n, this is going to be a to the n times b to the n. Okay. And you can extend this past two numbers inside the parentheses as well. Okay. So it's important to recognize that this is only true because of the things that are being multiplied. So I've mentioned before the common mistake of distributing that exponent over addition. So here you can distribute it over multiplication, but you can't over addition, right? This is not the same thing as a squared plus b squared as we've seen. This is a plus b times a plus b, and then you have to do the foiling or the distributive property or whatever you'd like to do. So it only works with multiplication or with division as well. So we can show it similarly for if you have a divided by b to the n, this will be a to the n over b to the n. And that's easy enough to show just using the same method. So maybe that's a good one just to try on your own, just to see if you can show these properties. Okay. All right, the next one, this one's called the zero rule. Okay, and this just describes what happens if you have a something to the zero with power. There's different ways to show this, but the way that I like to show it, let's just say that we have like x squared divided by x squared, and of course we're implicitly going to be assuming here x is not equal to 0, because again, we're introducing a denominator here. So on the one hand, this is, so I'm going to go in two directions with this. This is x to the 2 minus 2, right, from the quotient rule. So this is x to the 0. But on the other hand, we know that anything divided by itself is 1. So we have this string of equalities. So therefore, what we're getting here is that x to the 0 is equal to 1. And this did not mention anything about what x is, except for that it can't be 0. So this is the 0 rule, which is that anything to the 0th power is equal to 1 except for 0. Okay, so note that 0 to the 0 is indeterminate. Okay. So x to the 0 is equal to 1 as long as x is not 0. So 1 to the 0 is 1, 2 to the 0 is 1, etc. So another important one to keep in mind, we often have a tendency to see x to the 0 and think, oh, it's 0. But it's not going to be 0, it's going to be 1. Okay. In fact, there's no number that we can raise there's no exponent that we can raise a number to that will make it 0. Okay. And that'll be reflected on the graph as well. All right, so next we'll look at negative exponents. Okay, so what is a negative exponent? Okay. Okay, so if we just think of like 2 to the negative 1 or something like that. Okay, so this is just more of a definition rather than actually having to show it, but a negative exponent is defined as the multiplicative inverse of that number, which is another way of saying the reciprocal, which is another way of saying that we just flip the number over. Okay, so this is going to be 1/2. And when I say flip the number over, I mean that if we had 3/2 of the negative 1, we would completely flip the numerator and the denominator, 2/3. So this is called the reciprocal. So we take the reciprocal of the number. The reason that 2 becomes 1/2 is because any whole number can be thought of as the whole number over 1. So when you flip them, that 1 goes onto the top. Okay. More generally, if we have, not negative 1, but say just any exponent to the negative n, then this is going to be b over a to the n. So notice what's happening here. The negative part of this, the negative 1 part of it, is flipping the fraction, but we're still going to end up raising it to the n. Okay. The way we could think about this is that this is really to the negative 1 to the n, right? Using that power property, we can separate it, the negative 1 out of it. So we do the negative 1 power first, and then we do it just like we did the 3/2, and then you would also be raising it to the n, which we could then simplify to b to the n over a to the n, of course. Okay. So again, this is only going to be defined if a and b are both not 0. Anytime that we have a denominator involved, we need to make that disclaimer. Okay. So one way that we can kind of see this definition come to light is through the use of the quotient rule. Like if we look at h to the 3rd over h to the 5th, for example, again, on one hand, we get h to the 3 minus 5, which is h to the negative 2. And if we just look at what this would be with everything canceling, okay, then we have 3 copies of h canceling out. So we're left with 1 over h squared. So we get that h to the negative 2 is equal to 1 over h squared. So again, the rules are all consistent with each other, right? Okay, and then last but not least, we have the rational exponents. Okay, so we just saw negative exponents, we saw 0 exponents, we've seen whole number exponents. What about rational exponents? Meaning that there is a fraction in the exponent. So these are actually defined as roots. So things like the square root and the cube root and the 4th root, etc. These are the same thing as rational exponents. So 4 to the 1/2 power is equal to the square root of 4, which is equal to 2. Okay, you can try this out in your calculator. If you've never seen this before, you can do 4 raised to the 0.5 power, and you'll see that you get 2 because that's the square root of 4. So another example, 27 to the 1/3 power is the cube root of 27, which is 3. Okay, so again, these are just another definition. This is how the rational exponents are defined. In general, if we have something like, say, 8 to the 2/3 power, so here we don't have 1 on the top. The top number is the power, and the bottom number is the root. Okay, so we can have both the power and the root at the same time. So this would be the cube root of 8 squared, or equivalently 8 squared in the cube root of that. So the order doesn't actually matter. We can see that the order doesn't matter from the power rule. 8 to the 2/3 is equal to 8 to the 2 to the 1/3, right? Because you do 2 times 1/3. And this is equivalent to 8 to the 1/3 to the 2 times 1/3. So this is actually coming from the commutativity of multiplication combined with the power rule, the fact that we can do it in either order. And we can see that it works in either order here. The cube root of 8 is 2. So 2 squared is 4. And 8 squared is 64. And the cube root of 64 is also 4. Okay, so the order does not matter here. So the power is the top number. The root is the bottom number. Okay, so these are all of the exponent rules. Like I said, we'll see all these come up again with logarithms, and you can combine all of these rules as well. So it might be a good idea just to practice on, things like here. I'll actually just write one down here. Like maybe if we have 3, a to the 4th, b to the 7th time over 81, a b to the 9th, all to the say 3/4 power, negative 3/4. Just throw everything in there. Let's just look at how we would do a problem like this. So the problem might say something like simplify. Okay. So this is more of like just something, an exercise to practice the rules rather than something you practically would come across. But it's just good to kind of test out how you would approach the combinations of these exponent rules. And there's a few different ways we can approach it. So you could, distribute that outside exponent first to everything. You could flip everything over first. You could just simplify the inside first. So there's a lot of choice here. So why don't we just go ahead and simplify the inside first? Okay, so first of all, 3 over 81 is actually 3 to the 1 over 3 to the 4th. Okay, 81 is 3 to the 4th because it's 9 squared, right? And that's actually something you could also show with the exponent rules. 81 equals 9 squared. 9 is 3 squared. So 3 squared squared is 3 to the 4th. So we can use these rules to kind of come up with shortcuts like that. So this is going to be 1 over 3 cubed, or 1 over 27 if you prefer. So we'll get 27 in the denominator and the inside. A to the 4th divided by a will be a to the 3rd, 4 minus 1. B to the 7th over b to the 9th will be b to the negative 2. Okay, so you could write b to the negative 2 on the top, but that's just going to flip into the denominator. Okay, so we can go ahead and just put it in the bottom as b squared. And then we can do negative 3/4. So now maybe the next step we just flip everything because of the negative on the outside. And now it's just 3/4. And then we can just do 3/4 of everything, 3/4 power for everything. Okay, so we'll have, don't really need that anymore, 27 to the 3/4 b squared to the 3/4. So 2 times 3/4 because of the power rule. So we have 6/4. You can simplify that on the next step. And then a to the 9/4. Okay, so it doesn't look like we're really going to be able to make this much simpler, actually. So this one ended up kind of messy. That's what happens when I just make up numbers off the top of my head. We can see 6/4 is 3/2, so we can simplify that a little bit. But ultimately, it doesn't look like there's anything else we can do here. So this would be our final answer. Okay, 27 to the 3/4. I don't think there's a way to make that simpler because you can't take the 4th root of 27. So yeah, there shouldn't be anything else that we could maybe cube it first and then like simplify it a little bit, but you know, it's just kind of unnecessary. So I would just leave it like this.